Welcome to the class. My name is Alex. I think talk about parallel performance analysis. Let's start with the picture that everybody can know by heart. This is the top 500 performance by the year. This image is not that good. But what we have here is that if we look behind, if we look to the past 10 or 15 years ago, what we had was machines that were the number one in the world, and they are probably as fast as your notebook today. So what does this mean for us? First, we know that single core performance is pretty much done. We have been increasing the number of cores on our machines, and we have different things. We have GPUs, we have accelerators, we have all those kinds of things. So we should be taking the thing about parallel programming seriously right now. When we have this track of HPC here, HPC is only the people who find the problems first. The same problems that HPC people find today in 10 years is what people doing normal programming will find. So, besides that, it's not exactly getting easier. Parallel programming is hard, first, and we have new things. We have now those accelerators, we have GPU programming. When we get to faster scales, we always find new problems. We have also, with the increase of performance, we have increase of data. And no matter how fast we have machines, I/O is still a problem. Besides that, it's hard to understand what we have when we measure performance on parallel programming. For example, this is an old code called Sym3D. When we run it with 256 cores, or 256,000 cores, what each core does is pretty much the same. The rest is just waiting for communication. Of course, performance analysis is not something new. There are several of them, but when you start to get to the scale that we are today of petaflops and exaflops eventually in the next 5 years or so, most performance tools stop working. For example, Kojak is an old performance analysis tool. Is very old. It's not kept anymore, but it's like 16 years old. My group has a performance tool called Scalasca, which started in 7 years ago. And what's the idea of that? The idea is to have performance analysis that scales itself. Means that you have faster code. We have a tool that can actually go with your code. It's a work from the Research Center of Munich, Germany, which has one of the biggest supercomputers in Europe, and so it has to run there. What about it? It's new BSD. It's portable. It runs on pretty much everything. It runs on PCs with Linux, and it runs on the biggest supercomputers in the world. It supports Fortran, C++, it supports MPI, OpenMP, both. And what do you have that other performance tools done? Our analysis are scalable. They really go to high levels. We can search automatically for wait states in your codes. And we show reports of parallel performance. And more important than that, it's insightful. You can actually understand what's going on. What do I mean with insightful? Let's see an example of a code. This is a very simple code with another tool called Vampire, developed in Dresden, where one process sends a message to everybody answers, and this is easy to understand, right? But then, if you have a real code, it looks more like this, or this. And this. So it's not actually that easy to understand. So let me show you our workflow. What do we have? We have our source code. You instrument your source code. You have a binary. You run this binary. This binary will be measured. You have a summary report on it. And then it will have our GUI tool called Q that shows you what is the problem, where in your code, and in which process in the execution. With that, you reiterate, you optimize your measurements, and then you run a full trace of this thing to know all the problems of your code. As I mentioned before, and as I showed the picture, we are not alone. There are several other tools. The tools are different, but they have the same needs. Meaning, we need to measure, we need to instrument, we need to do a lot of things that are common. And this created a problem in our community, which was that we had a lot of people doing the same thing, essentially. And this is duplicated effort. So, duplicated effort is something that we don't like. No one likes. And another problem is that if you have all those measurements and all those different tools, you end up with a lot of measuring your code with different tools just because this tool might give you one insight, this other tool might give you something else. This is, of course, complicated. This is complicated for the sysadmin. This is complicated for the user. So what happens? For example, it was the state 2 years ago of some performance tools. You have Paraver, you have Vampire, you have Scalasca, you have Tau, and then you have converters between those tools. You have instrumenters of those codes. So this was very confusing for us. So what we did, we called the Romulans and created something called Scorpy. Scorpy is essentially, actually we have the original developer of something here. Thanks for coming. It's a community common project where we took all this common infrastructure of all those tools, what we need, which is common for all of them, and are developing this together. So we share the instrumentation system, we share the measurement system, we share the trace formats, the report formats, and so this, the idea is to unify effort, and so every group can build their own unique tools on top of it. So who uses that right now? We do in Uri, in Germany. People from Dresden use it. People from Munich uses it, and the people from the United States, from Oregon, use it. So again, what happened? We had this mess, and we cleaned up. What we have now is the instrumental module, a single trace format, and you just need one converter tool, and we have profiles and GUI. So, what do we measure? As I mentioned at the beginning, we measure MPI, OpenMP, and your functions. We can create MPI profiles. This is very simple. You just link your code against our library, and this runs really fast. It doesn't disturb your execution that much. This shows how many times the function was called, how much data was spent, how much time each function. It's like a profiler, but parallel. We can also create a callback profile, which means you can actually see who called who and when. This needs recompilation because we have to instrument the function calls. And this it creates, of course, some overhead. And so after running this, you might need to filter and just instrument some functions that you actually want to know about, especially in C++, for example. And then we have trace. Trace is when you can actually record every single event on your code. And then this can show you inefficiency patterns. But this, of course, this is heavy. This is heavy on data, and this is heavy on time. So this is important to filter. Our tool, it's parallel in the data collection, reduction. The analysis is parallel. It imitates your code. So if your code uses 1 million cores, our tool will use 1 million cores. We have everything parallel, well, except the visualization, but it's scalable. So what we measure? This is an example. Those are classic examples of MPI patterns. The first one is delayed sender, when a process took too long to send a message, and the other process are already waiting. So this delay, this waiting time is measured. You have late receiver, which is the opposite. You have wrong order, and you have barrier operations, and all those red arrows are delayed. So, for example, this is how our tool shows a late sender. It shows the problem, where in your code, and where in the machine which is running. In this case, a blue gene P. This is another way of viewing the thing, creating a topology of your application that maps your functions. So, for example, this code is code for measuring sea ice. As you can see, there is a lot of weights in the middle, close to the coast, because, well, there is no ice in those places. What else? We measure direct wait time. Means when you have someone sending a message and this wait of the other process spends, this time this other process spends on waiting, we can measure that. We can measure indirect waits. So, for example, what does it look like? Again, it's a matter of going to the GUI, seeing what we have as direct wait time. In this case of the example of sea ice, is a code from another research in Udemy. You see that direct waiting time, you have a lot around Antarctic and Arctic regions and on the coast, and you have little to no time on the sea. But the other hand, as you're not measuring any sea ice on the tropical part, you have a lot of indirect waiting time. What else? This was a very interesting research a couple years ago. Our tool is the only tool right now, as far as I'm aware of, that shows you where a delay was created. So if you have a delay in your code, might happen that this delay cascades and you have further delays. So our tool shows you where it started. So, for example, in process A at the beginning, you have a delay, and this delayed everything. This we have our tool shows. Besides that, we have, for example, one of the machines we use a lot is a Blue Gene Q. Blue Gene Q has a network of, it's a 60 torus network. It's hard to visualize 6 dimensions. So what we do is that we fold those dimensions, and we can still have some insights out of it. You can move them, you can select different ways of seeing them, and this is very interesting because, for example, the K supercomputer in Japan has also a 60 network. What else? Well, so where are we heading now? Energy, because my boss is getting tired of paying our electricity account, which is around 10,000 euros an hour. So we have to produce code that is aware of energy. Another thing is to bring performance analysis of parallel applications to the community. So what does it mean? As I mentioned in the beginning, we have the open source world is starting to need that. You have to program parallel right away. So that's why we are here. Seriously, we are here for that. And, well, essentially that's it. Any questions, we have a mailing list. There is a lot of very smart people wishing to answer your questions. And this is our website. Actually, that's it.
All right, any questions?
Yes.
Do you have any support for GPUs?
Yes, there is some initial support for CUDA already. We can measure CUDA events. but it's something that is already happening.
En wat is one of the applications that you said like that it's still on Scalasca
Yeah, you can get CUDA events and function calls for this dispatch. Also, we have already some initial support for the Xeon 5, which is also with the accelerator. Yes.
Question on that topic. On Scalasca, there was support for Xeon 5, but in Scorp E, that is completely it's not there.
It's not there yet. We are working on this.
What's the timeline on this?
It's ready when it's ready.
Oh.
I also have a question. Sure. So that you mentioned there are different performance tools out there, and now some of them are sharing a common base.
Yes.
Not everything yet.
Yes.
Do you still think it makes sense to have all these kinds of different performance tools that are each of them a little bit better in maybe some aspects?
Actually, yes, because there is no single answer. You might there are different, because performance analysis in itself today is more an art than a science, and so you have different things that you measure. So, for example, OR2 gives you a very straight answer to things, but if you want a more detailed, you might use a different tool. Or if you want different granularity, all those things are different. So yes, there are different goals.
So does it basically go from very user-friendly and not that much detail
To very specific, exactly. So if you try to do everything in one single tool, you have such a monster that, well, yes. Yes.
All right, thank you very much.
Thank you.